So today we are looking at the topic of power, and power is the rate of doing work. So if we think of something as a rate, we know that we are talking about an object as something in relationship to time. And so our equation for power is equal to work over time, or power is equal to the change in energy over time. So how much energy did we put in to make a task happen over the time it takes for that task to happen? And if we look at our units for power, power is measured in a watt, and 1 watt is equal to 1 kilogram times 1 meter squared. So if we think about kilogram times meter squared divided by second squared. So let's just think about that. We'll just, let me grab my pen here. So here we have joule per second, and we know that a joule is a Newton meter time divided by second. We know that a Newton is a kilogram times meter per second squared. All of this is times meters per second, right? That's what we've got here, newtons times meters per second. And so we end up with kilograms times meters squared kilogram times meter squared divided by seconds cubed. Okay. Let's keep talking about this a little bit. One of the things that we'll be looking at is efficiency, and efficiency is how effectively we are using our power. And so I'm just going to pull this up. And so efficiency is a measure of the ratio between how much energy we get out compared to how much energy we put in. We can also compare efficiency by using power, so the power we get out of an activity divided by the power we put into an activity. So we're going to look at example 6.11 or 6.11 from the textbook, and it's on page 325 if you're wanting to follow along in your textbook. So we have an elevator. Its occupants have a mass of 1,300 kilograms. The elevator and its occupants have a mass, so we're given our mass, and that's 1,300 kilograms. And the elevator lifts the elevator motor lifts the elevator to the 12th floor, and that is a distance, and so this is a vertical distance, and that's height is 40 meters in a time of 75.0 seconds. We're looking for A, the power, and essentially the power output of the elevator. This is the power generated as the elevator goes up, and B, we're looking for our efficiency. Okay, so I'm just going to pull up this image. This is the image from the textbook, and that should help us get a sense of what kind of work is being done here. We're doing work against gravity as we lift this elevator up, and so we're looking at how much energy does the elevator gain, and that energy comes in the form of gravitational potential energy. So our energy change is gravitational potential energy, and we calculate that using MGH. So we're going to calculate our power by looking at the change in potential, and let me just clean this up. Sorry, that's supposed to be the change in potential energy. So delta EP divided by our time, or the elapsed time, change in time. In this case, that's MGH divided by our change in time. So mass is 1,300 kilograms times g, which is our acceleration due to gravity, 9.81 meters per second squared, and our height is 40.0 meters. And all of that is divided by our time of 75.0 seconds. We do that calculation, and we get energy or power of 6,800 and 1.6 joules per second, or watts. Now, because this is an answer for part A, we need to quote this to 3 significant digits. We can round this to 6.80 times 10 to the 3 watts. We can also recognize that 10 to the 3 gives us kilowatts, so we have 6.80 kilowatts. Either of those answers is acceptable. Now we want to go on to B and calculate our efficiency. Remember, efficiency, E, and I'm just going to represent that by EFF, is equal to the power out divided by the power in. And if we go back up here and look at our question, the power in, or the power that the energy that the motor generated to do this work, is 9.40 kilowatts of energy. So our power in is equal to 9.0 kilowatts. Now, we've calculated the energy out, but remember, it's imperative that we don't use the rounded value, we use this unrounded value to calculate it. So we've got 6.8016 kilowatts divided by 9.40 kilowatts. And we can do this as long as the watt, we're using the same units. If you wanted to, you could convert both of those to watts and then do our division. Now we have, we divide that out and we get 0.724, and we can write that as 72.4% efficiency. Now we want to look at how power and speed are related. And recall that work is equal to force times distance. And if we apply that to the power formula, we know that we can insert the work into it. And what we come up with is, there we go, power is equal to force times distance, all divided by time. And we have distance here divided by time. And what that means is that we can take and look at force and multiply it by the average velocity to get our power. Now we're going to look at example 6.12, and that's on page 328 in the textbook. So page 328. And I'll read it through. A car of mass 2,000 kilograms is traveling up a hill at a constant speed of 90 kilometers an hour. And 90 kilometers an hour is 25 meters per second. The force of the air resistance, which opposes this motion, is 450 newtons. The slope of the hill is 6 degrees. So let's take and work our way through our givens. We have our mass, which is 2,000 kilograms. We have a velocity, which is 25.0 meters per second. We know that we have the force of the air resistance, and it opposes the motion, so that's negative 450 newtons. And finally, we know the angle, or theta, and that's 6.0 degrees. And so I'm going to show you the diagram, and we'll take a look at how we draw that. And just give me a second. And so this is the diagram from the textbook. I'm going to scroll up here a bit. And so notice that they've used F subscript F. They're using that, you probably think of that as the force of friction, and I believe that they're referring to that as the forward force. So I'm going to, instead of a subscript small f, I'm going to use a capital F there, and just so that we can distinguish it. Okay, so there's this forward force applied by the car to take it up the hill at this constant velocity. We know that we always have a normal force that opposes that is perpendicular to the force to the surfaces where the objects are forced together. Force of gravity always acts straight down. And finally, we have the air resistance acting backwards. And so we want to first draw our free body diagram. So let's just take this and assuming we've got here's our angle, and here's our object. We have our force of gravity acting straight down. Isn't that not so pretty? And we've got our forward acting force acting up the incline. And remember that up the incline is positive, down the incline is negative. We have our normal force that is equal and opposite to the perpendicular force of the force of gravity. So that's the component that acts down. It's the component of the force of gravity acting perpendicular to the plane. And here we have our force of gravity that acts parallel to the plane. We know that it acts here, pulling the car back down. That is the force of gravity that's parallel to the plane. And then we have our air resistance, which is acting down. Okay, and we notice that our net force in both instances is 0 because we have the car moving up the plane at a constant velocity. So if there's a constant velocity, there's no net force. And that lets us, or takes us to the place where we can add along the forces acting along the plane as the force of the air resistance plus the force of gravity, or the component of the force of gravity acting parallel to the plane, plus our force of friction. Now, these two are negative because they're acting down the plane, and the force of the forward force is positive, it's acting up the plane. So we can substitute in, we have negative 450 newtons. Here, we need to calculate this. Well, we know our angle here is 6 degrees. We know that our mass is 2,000. And so this parallel component is done by taking the force of gravity times the sine of the angle, because it's opposite that angle. We can calculate the force of gravity by using the mass times the acceleration due to gravity, again, times the sine of our angle theta. Okay, so let's substitute in our values for this. We have 2,000 kilograms times our acceleration due to gravity, 9.81 meters per second squared, times the sine of our angle, which is 6 degrees. Multiplying all of that together, and let me just pull out my calculator, and that gives us 2,050.8 newtons. And remember, this is negative because it's acting down the plane. So we have negative 2,050.8 newtons plus our forward force. And that's equal to a net force, which is 0. So I can add those two together. 0 is equal to 2,500.8 newtons, negative 2,500.8 newtons plus the force of friction, forward force. I move that force across by adding 2,500.8 newtons to both sides, and that gives me the forward force of 2,500.8 newtons, and we need to round this to 2 significant digits because our angle was to 2 significant digits, and so that becomes 2.5 times 10 to the 3 newtons. The next thing that we're asked to calculate is the power output of the engine. And remember, power can be calculated by taking the force that's been applied to maintain a constant velocity. And so in this case, we've calculated our force, 2,500.8 newtons, times our velocity in meters per second is 25.0 meters per second. And we calculate that out, and we come up with 62,520 watts of energy. We can write this in scientific notation to two significant digits, 6.3 times 10 to the 4 watts, or our other option is to go to kilowatts, and that would be 63 kilowatts. And now your textbook does it to 3 significant digits, but I think that's a mistake because the angle is 6.0 degrees given to 2 significant digits. I would encourage you to do some work on power out of the textbook. So let's just go to a new screen, and I'll give you some practice questions. So on page 328, there are the practice problems 1 through 4. I would encourage you to do those. And going back into the first example, there are 3 practice problems. That's on page 325, and so do those practice problems 1 through 3. If you do those and you decide that you need to do more, there are more practice problems in the workbook, and you just look up power there, and I'm going to let you go now. Thanks, bye.